Hey guys, Ms. Crumpacker here. We're going to start our next unit. It is oxidation reduction reactions and electrochemistry. It's also known as a redox reaction. So grab your packets and something to write with, highlighter if you choose, and let's get started. So by definition, an oxidation reduction reaction occurs when electrons are transferred between reactants to make our products. So we also call this our redox reactions. So basically what happens is I put two elements or compounds together, and in the process of making my products, they are going to transfer electrons around. So that's our definition of a redox reaction. So the classical definition of oxidation is either adding oxygen or removing hydrogen. So you can see on these examples how we go from iron and oxygen to make iron oxide. So we are adding oxygen, or hydrogen iodide is separating, and so we are removing hydrogen. Those are the classical way that an oxidation has been defined. Our more modern definition and what we will use is the loss of electrons. So a reduction reaction is going to be the opposite of an oxidation reaction by definition. In classical terms, it is the removal of oxygen or the addition of hydrogen. So again, you see this example here where I have iron oxide with carbon turning into iron and carbon dioxide. So I have removed the oxygen from iron. Or I have chlorine and hydrogen. They are coming together to make hydrochloric acid, so there I'm adding hydrogen. Or our more modern and what we will use definition is the gaining of electrons. So in an oxidation reduction reaction, these are always occurring at the same time. You can't have just an oxidation reaction or just a reduction reaction. So basically what's happening is one compound or element will be oxidized, and at the same time what it's reacting with will be reduced, or vice versa. So you can't have just one or the other. There's always going to be both of them happening at the same time. So to help us remember those definitions, we can use one of the following little sayings. You can use what we call oil rig. Okay, this is the one I like to use. Oxidation is loss of electrons, and reduction is gain of electrons. You can also use Leo the lion goes grr. So Leo and then grr. So lose electrons oxidation, gain electrons reduction. Whichever one makes sense to you and sticks in your brain, that's what I want you to use to help you be able to identify something as an oxidation or reduction in terms of reactions. All right, so let's answer this question. It says, when potassium loses or gains an electron, it becomes the ion K+. Well, if it's becoming K+, what's it doing? Is it losing or is it gaining? Well, if you know where potassium is, you know that it is losing an electron. Also, this positive tells you that it is losing an electron because the only thing that I'm going to gain or lose is electrons. So to become more positive, I have to get rid of negative charges, which is my electron. So does this mean that it is oxidized or reduced? So let's think about our little sayings. So I like oil rig. If I could spell, that might be beneficial. All right, so oxidation is losing, reduction is gaining. So is it losing or gaining? Well, it's losing electrons to become a positive ion, which means it is being oxidized. All right, so sodium in this example goes from a neutral atom to a +1 ion. Therefore, it has lost an electron and it was oxidized. Sulfur goes from a neutral atom to a -2 ion, therefore it gains 2 electrons and it was reduced. Well, how do we know this? Well, when an element is by itself and there is nothing written up as the exponent, it's neutral. But to form the Na2S, we have to know that they swap and drop our charges. Remember that from last semester. So sodium is an Na+1 because it's in group 1, and sulfur is an S2- because it's in group 6. So when they make Na2S, they are taking these charges and they are swapping them and dropping them down to form my Na2S. Sorry, my formatting seems to be off on my PowerPoint today. So what does that mean? Well, sodium goes from 0, there's no charge here, to +1 whenever it makes its compound, okay? So it's losing an electron in order to do that. That means it's oxidized. Sulfur goes from 0, because there's no charge and it's by itself, to a -2, which means it's gained 2 electrons. Therefore, it was reduced. So the easiest way to determine which element's oxidized and which element is reduced in a reaction is to assign their oxidation numbers to them. Most of our elements are going to have their same oxidation numbers that we have always learned and used. There are a few rules that we will follow, but for the most part, our oxidation numbers are going to follow the same trend across the periodic table that they always have. So when I say oxidation number, I'm talking about the charge that they will have. So remember, when you have your periodic table, okay, remember we did +1, +2, +3, plus or minus 4, -3, -2, -1, and 0. Those are the charges I'm talking about, okay? So many of these charges will still be the same, but there are a few rules that we will follow that might alter the charges oh so very slightly. So in this question it says when lead loses 4 electrons, it takes on a charge of what? It takes on a charge of 4 plus, or +4. If it's losing electrons, it's going to become positive. Okay? If it gains electrons, it becomes negative, because remember, your electrons are your negatively charged particle. So does this mean that it is oxidized or reduced? So again, we're going to look at our little saying of oil rig. I don't know why I keep trying to put a G first. Oil rig, so oxidation is losing, so it is oxidized. All right, so let's go over a few rules that we need to follow for assigning our oxidation numbers or our charges. You might want to make yourself a note. Okay, so these are your charges that are on the periodic table. All right, so rule number 1, all free elements are assigned the oxidation state of 0. So this is elements by themselves. So if you see iron by itself as a solid, it's a free element, its oxidation state is 0. If you see a diatomic, its oxidation state is 0, okay? So anything that we have classified as a free element will always be a 0 charge. Number 2, the net charge of a compound is equal to the sum of the oxidation numbers in all the compounds. So if I have a compound that is saying, let's say it's like CO2, CO2 is a neutral compound, so that means my carbon and my 2 oxygens, their positive and negative charges are going to equal out to 0 because CO2 is a 0 compound. However, if I have, let's say I have a polyatomic like ammonium, it's NH4 with a +1 charge. So that means my nitrogen and my 4 hydrogens are going to add up together their positive and negative charges to equal an overall +1. So that's going to help us keep track of things that don't have set rules. All right, your alkali metals, this is your group 1 metals. They are always going to be a +1, which is the same rule that we've always known. Your alkaline earth metals, so this is your group 2. These are always going to be an oxidation number of +2. Zinc and cadmium, those are those transition metals that we had said had a set single charge. Those are also going to have a +2 assignment always. Okay, so the next one is halogens. Halogens, this is your group 7. A, okay? These are always going to be assigned a -1 charge. Hydrogen in compounds is going to be assigned a +1 charge, and hydrogen's in group 1, so easy. Except in hydrides where it's a -1. We're going to kind of ignore some of these exceptions. Occasionally they'll pop up, but don't completely get rid of it. Just know that you're not going to see them super often. We try to be nice to y'all in this unit. Oxygen in a compound is assigned an oxidation number of a -2, except in peroxides where it's a -1. Again, these exceptions are not going to happen super often. Any remaining atoms are assigned oxidation numbers after all the other elements. So you need to go through and do everything that has a specific rule first, and then you can do the other atoms that are left over. All right, so my formatting's a little off and I had to hide some things that I couldn't hide before. So let's do these examples together. It says, give the oxidation state for each element in the following molecules. So what we're going to do is we're going to look at our rules and follow those first, and then if anything's left over, we will go from there. So HCl is not a free element because it's in a compound, so we're going to ignore number 1. Number 2 says the net charge of the compound is equal to the sum of the oxidation numbers. So the net charge of this compound is a 0, so that means that I need to equal 0 for this compound. So then from there it says alkali metals and compounds are always assigned a number of +1, and hydrogen is an alkali. It's actually not an alkali metal, but it's over there in that group. And hydrogen does have its own rule, and it's assigned an oxidation number of +1. So I'm going to assign that one first because hydrogen has a specific rule. Chlorine is in here as well. Now chlorine is a halogen, so it is in group 7, so it's a -1. So if you notice, my +1 for my hydrogen plus my -1 for my chlorine gives me a net charge of 0. So when you are assigning these, you literally just have to write the charges above them. So hydrogen's +1, chlorine's -1. So here I have P2O5. I'm going to rewrite this just because my formatting is a little off. Okay, so P2O5. Now notice I'm in a compound, so I don't have any free elements, and my net charge overall is 0. So what I need to do is I need to look at these and assign their specific numbers. Now, phosphorus does not have a specific charge. It doesn't have a rule, but oxygen does. So you always assign the ones that have a rule first. Since oxygen has a rule, I'm going to assign its charge, and it is a -2 charge. Now, the next thing I need to look at is how many are there? Well, there's 5 there. So I have 5 oxygens at -2. Okay, well 5 oxygens at -2, that's a -10. Okay, so a -10 plus something needs to equal 0. Now, the next thing I need to look at is phosphorus. I don't know what it is, but I have 2 of them. So I know that there are 2 of some charge and it needs to equal 0. So I need to figure out what that something is or what my x is. So if I do that, then what I can do is I just do a little rearranging of my equation here, and I get that x is equal to a +5. So P2 is +5. Now, it is really important that you have your positive and negative on the numbers. Don't just put 2 and don't just put 5. It needs to show whether it is gaining or losing electrons, and that positive and negative tell you that. Okay, so I want you to pause the video and I want you to do the next one, which is H2O. Alright, so hopefully you got hydrogen as a +1 and oxygen as a -2, and notice that they both equal 0 when you add those 2 sets of charges up. Now the last one is O2. Again, my formatting got crazy. Well, O2 is a diatomic, okay, and it's also a free element. So well, it's a free element because it's a diatomic. So overall, our net charge is 0, okay, which means its oxidation state is 0 because it is a free element. All right, so let's try these next ones. I have NH4 plus. So notice that my overall charge for this is a +1, not a 0, is a +1. So that means my two different elements here need to add up to a total of +1. Well, I have 4 hydrogens, and hydrogen has a set rule of +1. So I have 4 +1s, and then I have 1 nitrogen, so just X. So I have +4, I need to get to a +1. How do I do that? Well, I gotta subtract 3, right? So -3 will get me to that, and so my charge for nitrogen is a -3. Next one is MnO2. So again, oxygen has a set charge. My overall for this compound is a 0. Oxygen's set charge is always going to be a -2, and there's 2 of them. So I have 2 -2 charges, and I have 1 of something unknown. So 2 times -2 is -4. So to get 0, I need to add 4. Okay, so manganese is +4. Next one is Na2SO4. So here, again, I have, this one can be a little bit trickier because I have more than just 2 elements. Okay, so I have to really follow the rules here. So I have an overall charge of 0. Oxygen is always going to be a -2, and there's 4 of them, so 4 -2s. Okay. Sodium is in group 1, so it also has a set rule of +1. So I have a +1, and then I have something that I don't know. Oh, I have +1, but I have 2 of them. I missed that. So I have 2 +1s, and then I have my sulfur, which I don't know the charge for. So the 4 -2s gives me a -8, and the 2 +1s gives me a +2. So right now I'm sitting at a -6, because +2 plus -8 is -6. So that means X needs to be, in order to get to 0, a +6. So sulfur is a +6. All right, so I want y'all to try these next 3 on your own. I will put the answers up, so go ahead and pause the video, and I want you to go through the rules and try the next 3 on your own. All right, so hopefully you got the same answers that I did. I have aluminum as +3, phosphorus as +5, and oxygen as -2. And the next one I have calcium as +2, oxygen as -2, and hydrogen as a +1. And then I have on the last one titanium as a +4 and oxygen as a -2. All right, so another way you can look at this is that oxidation is increasing the oxidation number, and reduction is decreasing the oxidation number, so it's reducing it. The oxidizing agent is a substance in a redox reaction that accepts electrons. It is a substance that is reduced. So you're going to notice in this unit that everything is the opposite. So oxidizing is losing electrons, and when it loses electrons, its oxidation number becomes more positive. Okay. And reduction is gaining electrons, so it is decreasing its oxidation number or becoming more negative, which means that the thing that reduces is causing the other thing to oxidize, and the thing that is oxidized is causing the other thing to reduce. So the oxidizing agent is the substance that causes the other substance to oxidize. And in the process of that, it is reducing, itself is reducing, because it is taking away electrons and becoming more negative. And the other thing that it's taking from is losing electrons, therefore is oxidized. So oxidizing agent is the thing that's reduced, and the reducing agent is the thing that was oxidized, because it is giving away its electrons. So again, they're going to be opposites of each other. Oxidation and reduction are opposites of each other. They are caused by the opposite element in a reaction. So something to note here, when we are labeling things that are oxidized and things that are reduced, only an element can be reduced, but the entire compound is the agent, okay? Only an element can be oxidized, but the entire compound is the agent. So that is really, really important. That is a common mistake that happens, is students try to make the agent be an element and the thing that's being oxidized or reduced be the compound. No, the agent is the compound. It's the whole thing, okay? And it is making individual elements do oxidizing or reducing. All right, so I had to redo my thing because my formatting got even crazier on this page. So this is a reaction that you have on your packet. It says identify the element oxidized, the element reduced, the oxidizing agent, and the reducing agent. Before we can do that, we have to, number one, assign numbers. So we're going to assign oxidation numbers to every single thing in this compound. Okay, so just like we did in the previous slide where we were just doing single compounds, we're going to do that, but we're going to do it across the whole thing. Okay, so manganese, well, let's do the things that we know have a rule first. So do your hydrogens, your oxygens, your group 1s, your group 2, and your group 7. So oxygen has a rule. It is always a -2. Hydrogen is a +1. Chlorine is a -1. In this particular activity, this reaction, redox reaction, do not worry about your coefficients. We don't care about those. We just care about if I have a single compound, what is its charge. All right, so chlorine is a -1 because it's in group 7. When it's in a compound, when it's by itself, Cl2 is a diatomic, it's 0. Here, hydrogen's +1, oxygen is a -2. All right, so now we need to go back and we need to look at the things that didn't have a set rule, which in this case, all that's left is manganese. So oxygen, here I have -2, but there's 2 of them. And so because I have a -2, and 2 times -2 is -4, so to make it 0, I need a +4. Over in the other compound where manganese resides, notice that it is with chlorine as a -1. So because it's a -1, there's 2 -1s, so a -2, which means that to make it 0, this needs to be a +2. All right, so this is where students tend to get confused because they're like, Ms. Crumpacker was +4 on one side, why is it -2 or +2? That's because it is either oxidized or reduced. That's the whole point of this unit, is we are seeing that our charges are changing from my reactants to my products. All right, so notice what you're gonna do is you're gonna say, okay, manganese went from a +4 to a +2. So we know that there was a change in that area. And then we're going to look, oxygen is the same, hydrogen is the same on each side. Chlorine, though, goes from a -1 here, and it's still -1 in the compound, but it's also by itself, so it changed right there. So we're going to compare these chlorines to each other, and we're going to compare these manganese to each other. So manganese starts as a +4, and it goes to a +2, okay? And then chlorine starts as a -1, and it goes to 0, okay? So on manganese, it goes from +4 to +2, which means it's gained negative charges. Its charge has gone less positive. So it has gained 2 electrons, okay? And chlorine goes from a -1 to a 0, so it becomes more positive, which means it's lost electrons. So it has lost 1 electron, okay? So now we're going to look at our oil rig, or Leo the lion, and you're going to say oxidation is losing, reduction is gaining. Well, which one lost? Chlorine lost. So this one is oxidized. Chlorine is oxidized. And so reduction is gaining. So the gaining of electrons means that this was reduced. Okay, so now the last thing is it wants to know the agents. Well, it's going to be the opposite. So if it was reduced, that means that this is the oxidizing agent. It's the thing that caused the other one to lose electrons by gaining them, which means that if it's oxidizing, okay, so I said that backwards, oxidizing agent, this is going to be the thing that causes the oxidation, not just the manganese. It is where manganese resides. Manganese is in MnO2, is the oxidizing agent. So chlorine is oxidized, which means that it is going to be part of the reducing agent. Okay, so that means that I need to find the compound where chlorine was. Well, it was in HCl. Okay, so your oxidizing agent is the compound where the thing that was reduced, manganese, where it was hanging out. And then the reducing agent is where the thing that was oxidized, chlorine, was hanging out. Okay, so for this one, we're going to do the same thing. We are going to assign oxidation numbers, so for everything in this reaction, and then we're going to identify the element that's oxidized, reduced, and then the 2 agents. All right, so copper is by itself, free element, 0. We're going to go through and we're going to assign everything that has a rule. So hydrogen is a +1, oxygen is a -2, copper we're going to ignore because it's in a compound now, so it's not a free element, but oxygen, +2. Here, oxygen is, why did I put +2? Silly me. -2, okay? Over here in NO2, it's also a -2. Hydrogen is a +1. Oxygen is a -2. All right, so now what we need to do is we need to go and do all the things that have rules. Now, there's a couple of ways you can handle this, or all the things that don't have rules, but to add up to what we need. So here in NO2, oxygen's a -2. There's 2 of them, so -4, which means nitrogen needs to be a +4. Okay, over here in the copper nitrate, I don't know what nitrogen is, and I don't know what copper is, but remember the trick whenever we were writing compounds and we swap and drop, you can unswap and drop, so uncrisscross, and that will tell us that our copper is a +2 over here, which means I can then figure out my nitrogen. So oxygen is a -2, there's 3 of them, but there's 2 nitrates here. So that means there's 6 oxygens at a -2, so there's -12. And then I have 2 nitrogens, and then I have a +2 on my copper. So I have -12 plus 2 is -10. -10 divided by 2 is will leave me as a +5 for nitrogen. Okay, and then over in this other hydrogen nitrate or nitric acid, I have -2, there's 3 of them, so that's -6, and then I have a +1, so a -5, so that means nitrogen needs to be a +5. So now what we're going to do is we're going to look at everything that changed. So copper went from a 0 to a +2, so that made a change, okay? Hydrogen went from +1 and it's still +1. Nitrogen went from a +5 here to a +5 and then a +4. So nitrogen made a jump. Okay. And then oxygen stayed the same. All right, so we are going to compare copper to itself, and we're going to compare nitrogen to itself. So for copper, it went from 0 to +2, and nitrogen went from +5 to +4. All right, so this one, this is where we get our oil rig again. So oil rig, or Leo the lion. So copper went from 0 to +2. So that means it became more positive, which is the only way to do that is losing electrons. So it lost 2 electrons, okay? And nitrogen went from +5 to +4, so it actually got more negative, which means that it gained 1 electron, okay? So now we can use our oil rig. Oxidation is losing, so that means that copper was oxidized. And nitrogen is gaining, so that means it was reduced. So now we're going to look and we're going to say, okay, copper was oxidized. What was it in to begin with? Well, it was just by itself. So copper is going to be your reducing agent. Okay. We're going to now look at nitrogen. What was it in to start the reaction? It was in HNO3. So that is the oxidizing agent. So for the next set of examples, I want y'all to do exactly what we just did together. I want you to write the oxidation number of the elements, tell whether it's oxidized, reduced, and which ones are your agents. So you have magnesium plus oxygen, yielding magnesium oxide. You have silver nitrate plus copper, yielding copper nitrate and silver. Then on the next set, you have CH4 plus O2, and then you have Fe2O3 plus carbon. So I want you to go through and I want you to determine what is reduced and what is oxidized, what is your reducing agent, what is your oxidizing agent, and in order to do that, you do need to write the oxidation numbers across the top. That will be an expectation moving forward. So I know my formatting's a little crazy. It's not as bad as it was, but it's still a little crazy. So here you have magnesium and oxygen. These are both free elements, okay? Oxygen -2, magnesium +2. So in this case, oxygen is reduced and magnesium is oxidized. Like I said, it's a little crazy. This is oxidized. This is reduced, which means that your oxidizing agent is O2 and your reducing agent is Mg, okay? And the next one, copper is oxidized, silver is reduced, your oxidizing agent is silver nitrate, your reducing agent is copper. We're going to do the same on this one. I will fix the formatting as best as I can. Carbon is oxidized, oxygen is reduced, your oxidizing agent is O2, your reducing agent is CH4. And the other one, carbon, again, is oxidized, iron is reduced, your oxidizing agent is the iron 3 oxide, and your reducing agent is the carbon. All right, so now that we have figured out how to determine whether something is oxidized or reduced, we're going to get into something called electrochemistry. Electrochemistry is the conversion of a chemical energy into electrical energy, and it's involving the transfer of electrons. So this usually occurs in a device called an electrochemical cell or a battery. So I don't know if y'all remember the activity series from last semester, our hot or not list. We are going to use that activity series to determine whether a battery cell is very effective or not, okay? So electrons are lost by our more active metals, so the hot metals, and gained by the less active metals, or the not metals. The higher the metal is on the activity series, the easier it is to oxidize. So to simplify, our most reactive to our least reactive, group 1 and 2 metals are our most reactive, followed by aluminum, then our transition metals, hydrogen, and finally our jewelry metals. All right, so my formatting is way crazy. I have no idea what's going on. All right, so let's practice. Looking at your activity series, you're going to decide what is more active between the two pairs. So iron or copper. If you look, copper is here, and then iron is here. So which one's higher? Iron. Okay. Calcium or silver. Well, calcium's up here, silver's down here. Calcium. Silver or hydrogen. Here's hydrogen, here's silver, so hydrogen. Hydrogen or sodium. Sodium. And then zinc or cadmium. So here I have cadmium, here I have zinc. Zinc is higher, so zinc. All right, so batteries are electrochemical cells that convert chemical energy into electrical energy. We also call these voltaic cells. The energy is produced by a spontaneous redox reaction. Voltaic cells can be separated into two half cells. A half cell consists of a metal rod or strip immersed in a solution of its ions. So here we have an example. I have a copper metal strip, and it is in a water solution of copper sulfate, so its own ions are in that solution, and it is connected to another strip of a different metal, zinc, which is also in a solution of its own ions. All right, so you need to be able to label and know the voltaic cell and what things are on each side. So the anode and the cathode. So the anode is going to usually, not always, but typically be on the left-hand side of a diagram, and the cathode is on the right-hand side, but not, again, not always. Direction of electron flow is always going to be anode to cathode. Okay, so it's always going to go from in alphabetical order. Okay, so from A to C. The half cells are connected by something called a salt bridge. This is a tube containing a solution of ions. These ions pass through the salt bridge to try to keep everything balanced. The electrons will pass through an external wire, and then the metal rods on the voltaic cell are called electrodes. Oxidation occurs at the anode, and reduction occurs at the cathode. So a way to remember that is an ox, so anode oxidation, and red cat, so reduction cathode. The direction of electron flow is always going to be from anode to cathode. So a way we can remember that is fat, cat. Okay, because your cathode is getting more electrons. All right, so it says write the half reactions to show what happens in each part of the cell that occur. So here I have iron, Fe2+, and nickel, Ni2+. So here we need to look at our list, and we need to decide, okay, which one is higher up on the list and which one is lower on the list, because that's going to tell us which one is gaining electrons and which one is losing electrons. So turn to your activity series. I think you have one in your notes, and let's look and see which one is higher. So find iron and find nickel. All right, you'll notice that iron is more reactive, and so it tends to lose electrons, whereas nickel is less reactive, so it's going to gain the electrons. So if iron is losing the electrons, what that means is I'm going to have Fe is going to become Fe2+, and its 2 electrons are going to be removed, okay? Whereas my nickel is my less active, so it's going to gain electrons. So it's going to start as its ion so that it can gain those electrons. So nickel 2 plus 2 electrons is going to give me my uncharged nickel. So you will notice you have a chart in your packet that has half reactions on it, and it will tell you that these are the standard reduction potentials. So it's showing all of the reduction reactions. Well, the oxidation reaction is just the opposite, okay? And so if you just reverse that reaction, then you have everything that you need to write a half reaction. You just need that chart. All right, so again, let's do this. We have zinc 2 plus and copper 2 plus in our cell, and it wants us to write the half reactions for this. So again, we need to figure out on our chart which one is higher, zinc or copper. In this case, if you look, you'll notice that zinc is higher. So zinc is going to be losing electrons. So we're going to write zinc is losing electrons. And it tells you in the question that it's losing 2 electrons, okay? Which means that copper is going to be gaining those 2 electrons. Okay, so again, you're just going to, they're opposites of each other. Everything is opposites in this unit. So they're just going to be flip-flopping who gets the electrons and who gives them away. So here we have our cell potential table. So if the half reaction you're looking for is essentially written backwards, you're going to rewrite it in the way you need it and then change the sign of the cell potential. So if we just look, these are all reduction reactions. So it is called a standard reduction table. So if you need it to be an oxidation reaction, you just flip the reaction and flip the sign of the cell potential. So let's say that your half reaction looks like H2 plus 2OH yields H2O plus 2 electrons, but on the reaction table it looks like what is shown. Then what we would do is we would just change the sign of our cell potential in order to make it work for the reaction that we need. So a common battery is made with nickel and cadmium. What is the cell potential of this battery? Well, first we need to write our reactions. So cadmium's oxidized. So it's going to be cadmium yields cadmium 2 plus 2 electrons. And nickel is reduced. So it's going to be nickel 2 plus 2 electrons. And you'll notice the nickel reaction looks the way it does on your chart. The cadmium reaction is the opposite. Okay, so if we look then at the cell potentials, cadmium is originally a minus, let me find it. Found it. It is usually a negative 40, but since we reverse the reaction, it's going to be a positive 0.4. Okay, and then nickel, because it's exactly the way it's supposed to be written, we're just going to keep it the same. So it's a negative 0.25. So we're just going to add those two values up. So a positive 0.40 plus a negative 0.25 gives us a cell potential total of 0.15 volts. Okay, and it's going to be positive. You want positive cell potential or you have a dead battery.